All right, we're going to look at section 5.2, which is on a couple rules of probability. We're going to look at the addition rule and the rule of complements. So first of all, we need to talk about what a compound event is. A compound event is an event that is formed by combining two or more events. So we looked at some compound events in the last section. If you remember the question about the number of children a woman has, when they asked if they have less than 3 children, that was a compound event because that included 2 children, 1 child, or no children. So let's look at another example. Let's say you're rolling a fair die. If event E is rolling a 2 or a 3, that's a compound event because there's more than one outcome, or like event 1 could be rolling a 2, event 2 could be rolling a 3. So for event E, we're combining those 2 events together. And what we want to look at for the general addition rule is to look at the probability of A or B occurring. And this word or is super important. That's when you know that you're going to be using the addition rule, which I'll get to in a second. But what this means when they ask you that, define the probability of A or B, it just is the probability that A occurs or B occurs, or they both occur. That's what A or B means. And we'll be distinguishing between or probabilities and probabilities. And an example that I like to use to help students see the difference is, imagine that you're reading the want ads in a paper or a journal or something. And the ad says that you need a college degree or 5 years experience. Well, let's compare that to if the ad said you need a college degree and 5 years experience. There's a big difference. With the or, you could have the college degree and no experience and still be qualified. You could have the 5 years experience and no college degree and still be qualified, or you could have both and still be qualified. But if the ad said that you need a college degree and 5 years experience, you've got to have both of them. And in the next section, that's where we'll be talking about and probabilities. Okay, so for our example, where we're rolling a fair die and event E is rolling a 2 or a 3, then the probability of event E would be, there's one way to get a 2 and there's one way to get a 3. So there are 2 ways out of 6 total, which is 1/3. So there I didn't use any special rule. I just counted the number of ways event E can occur and divided by the total number. You can keep doing that, that's fine. But there might be situations where you actually need to use a rule or a formula. So I'm going to tell you what that formula is, and then we'll go back and do this example using the formula, although we know it's not necessary. And what the general addition rule says is, if you are looking for the probability of A or B, and again, we're going to use this or is that indication that you're using the general addition rule. Well, it's equal to the probability of A plus the probability of B minus the probability of A and B occurring at the same time. Now, if you read this rule in the book, they just say the probability of A and B, but I find that that can get confusing with what we're doing in the next section. So I always like to emphasize that it's occurring at the same time. So The reason, so we're taking all the ways that A can occur and finding that probability, all the ways that B can occur and finding that probability. Some of those may overlap. There may be some where A and B happen at the same time, so you're counting them twice. So that's why we have to subtract the probability that they occur at the same time. So let's rework this example using the general addition rule. So we're going to roll a fair die, and we want to find the probability of rolling a 2 or a 3. So we want the probability of a 2 or a 3. Well, using the general addition rule, that's going to be the probability of the first event plus the probability of the second event minus the probability that the two events occur at the same time. So that would be rolling a 2 and a 3 at the same time. Okay, well, the probability of rolling a 2, we saw in the last section, is 1 out of 6. The probability of rolling a 3 is 1 out of 6. Minus, now you're rolling the die just once, so when you roll that die, there is no way that you're going to get a 2 and a 3 at the same time. You can only get one number. You're just rolling one die. And so that is 0. And sometimes that will happen, that where it's impossible for the two events to occur at the same time. And so that leaves us with 2 out of 6, which of course is 1/3. And the same thing we got just doing it by counting earlier. Now when this happens, when this is equal to 0, we say that the two events are mutually exclusive. And we'll formally define that, but it just means that it's impossible for the two events to occur at the same time. So let's go ahead and define that. So mutually exclusive means that it is impossible for two events to occur at the same time. We can look at this in terms of a Venn diagram if you're more visually inclined. So with a Venn diagram, what we're saying is when they're mutually exclusive, if this circle represents event A and this circle represents event B, there's not going to be any overlap at all. They're two totally separate events. So that would mean that these are mutually exclusive. Now, if there is some overlap, so like if this is event A and this is event B, then this would be where they are not mutually exclusive. There's some sort of intersection between the two sets. So we'll talk some more about that when we get to the examples. All right, I have one last thing to define, and then we'll be ready to work some examples, and that is the complement. Now the symbol for the complement is A. Like if we want A complement, it's A with a little C written beside it. So this is red A complement. Another notation that you'll sometimes see in books is A prime, A with a little prime beside it. This book uses the C, but just in case you've seen this before, that's another way to denote it. And it is just simply the opposite of A. So if you remember that example we did with the bills and whether they were paid on time or not in the last section, the probability, if event A was the bill was paid on time, then the opposite of A would be the bill was paid late. And so that would be A complement. So let's look in terms of our example that we've been using, rolling a fair die. If A is rolling a 2 or a 3, event A would have this sample space. Then A complement would be the opposite of that, so that's not rolling a 2 or a 3. And so the opposite would be rolling a 1, 4, 5, or 6. And so that would be A complement. Notice with these, if we were doing probability, and I pointed this out on the bill example as well, but let's look at it here. If we wanted the probability of A rolling a 2 or a 3, we did that earlier, that was 2 out of 6, or 1/3. Now notice that if we wanted the probability of A complement, well, there are 4 ways that A complement can occur, so that's 4 out of 6, or 2/3. And notice that these two probabilities of the complements, if you add them together, 1/3 plus 2/3 is 1. So the sum is equal to 1. And that will always be true when you're dealing with an event and its complement. And so we have something called the rule of complements, which says that if you have the probability of A complement, you can find that by taking 1 minus the probability of A. And vice versa. If you want the probability of A, you can find that by taking 1 minus the probability of A complement. Sometimes it's going to be easier to use the complement to find a probability. And we'll look at some examples and I'll point out how it's easier. Sometimes it doesn't matter. Like on this example that we just did, we easily found the probability of A complement without doing the subtraction, but notice it would have worked. If we were doing the probability of A complement, it should equal 1 minus the probability of A. So that would be 1 minus 1/3, which leaves us with 2/3. Okay, so let's take a look at some examples from the homework. And we'll use our rules that we've been learning. So on page 216, let's start with number 14. It says if the probability of A is 0.45 and the probability of B is 0.7 and the probability of A and B, and what they mean there is occurring at the same time. They just don't say that. I wish they did. I think it would clarify things. But that's what they're talking about, is 0.65. Find the probability of A or B. Okay, so they want us to find the probability of A or B. So as soon as you see that word or, you should think about the addition rule. And so the addition rule is going to be the probability of A plus the probability of B minus the probability of A and B at the same time. Okay, so the probability of A they gave to us, that was 0.45. The probability of B they gave to us, that was 0.7, minus A and B at the same time. They gave us that probability, that's 0.65. So you're just going to take 0.45 plus 0.7 minus 0.65, and you should get 0.50. And so that's the probability of A or B. Let's look at number 18. It's kind of similar, although we're going to answer a question at the end. It says, if the probability of A is 0.5 and the probability of B is 0.4 and the probability of A or B is 0.8, are A and B mutually exclusive? Okay, well, let's think back to what mutually exclusive means. If two events are mutually exclusive, then the probability of A and B at the same time is 0. because it can't happen. So what we're going to do is plug these values they give us into the addition rule and see if the probability of A and B at the same time is 0. If it is, then they are mutually exclusive. If it's not, then they're not mutually exclusive. So going back to the addition rule, we have the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B at the same time. Okay, so the probability of A they gave us, it's 0.5. Probability of B they gave us, it's 0.4. And the probability of A or B they gave us, that's 0.8. And that goes on this side. And we're going to subtract the probability of A and B at the same time. And basically we're just looking to see, does this equal 0? That's the question. Well, we don't even have to finish solving for it. You'll see here that we have 0.8 equals 0.9 minus the probability of A and B at the same time. If this were 0, then these two numbers right here and right here would be the same, and they're not. So there is no way that this is equal to 0. So we can just say not equal to 0. So to answer the question, no, they're not mutually exclusive because there's going to be a value there. Now you can finish solving for it and see that it would be 0.1. So it's not 0. Okay, let's take a look at number 22. Now, when I copied this over from the textbook, I didn't copy it correctly. What that means is the probability of B complement. I didn't leave that superscript. Is equal to 0.64. They want us to find the probability of B. Well, we can use the rule of complements. The probability of B is always equal to 1 minus the probability of its opposite. So B complement. So the probability of B is going to be 1 minus 0.64, which gives us 0.36. So that would be the probability of B. Okay, now we're going to look at an example, and we want to decide if they're mutually exclusive. And remember, the determination for mutually exclusive is that they can't happen at the same time. So event A is Jaden has a math class on Tuesdays at 2 o'clock. Event B is Jaden has an English class on Tuesdays at 2 o'clock. So you want to ask yourself, can those two events happen at the same time? Well, not usually. Usually you can only enroll for one class at one time. So these are mutually exclusive. Jaden cannot have a math class at the same time as an English class. So they're mutually exclusive. Okay, let's now calculate some probabilities and some real-life examples. So for number 36, it says, let V be the event that a computer contains a virus, and let W be the event that a computer contains a worm. Suppose that the probability of V, I'm just going to jot these down so we have them right here in front of us, is 0.15, so that's the probability of a virus. And then the probability of a worm is 0.05. And then the probability that the computer has both a virus and a worm at the same time is 0.03. Okay, so keeping those in mind, for part A, they want us to find the probability that the computer contains either a virus or a worm or both. So or. We're going to be looking at the general addition rule. So we're looking at the probability of V or W. So the addition rule tells us that this will be the probability of a virus plus the probability of a worm minus the probability of a virus and a worm at the same time. Well, they gave us all of those values, so it's just going to be a matter of plugging it into the general addition rule. The probability of a virus is 0.15 plus the probability of a worm is 0.05 minus the probability that the computer has both of them at the same time is 0.03. And so 0.15 plus 0.05 is 0.2 minus 0.03 is 0.17. So that's the probability that it has one or both of those problems. Okay, for part B it says find the probability that the computer does not contain a virus. Well, does not contain a virus is the opposite of having a virus. So having no virus is the opposite of having a virus. So it's the probability of virus complement or V complement. And so using the rule of complements, that's going to be 1 minus the probability that it does have a virus. So that will be 1 minus the 0.15, which gives us 0.85. So there's an 85% probability that the computer does not have a virus. Okay, let's take a look at number 40 now. It's on statistics grades. In a statistics class of 30 students, there were 13 men and 17 women. 2 of the men and 3 of the women received an A in the course. A student is chosen at random from the class. So I always like to just jot down what they give us so I don't have to keep reading the problem. So we have 30 total. There are 13 men and 2 with A's. And there were 17 women, 3 with A's. And we're selecting 1 student. I'm emphasizing that right now because in the next section we're going to look at when you're selecting more than 1 item. So when you're selecting just one, we use different rules than when you're selecting more than 1. Okay, so for part A, find the probability that the student is a woman. Well, they're not asking anything about the grades. We just want overall the probability that it's a woman. So the probability that it's a woman is the number of women, which would be 17, out of the total number, which is 30. And so if I convert that to a fraction, I'll take 17 divided by, or convert it to a decimal, I'll take 17 divided by 30, and so that's 0.5667. So that's the probability that the student is a woman. Okay, now for part B, find the probability that the student received an A. Well, they're not differentiating between men and women. We're just saying what's the probability that someone got an A. So if you look back at our information, there were 5 students total with A's, 2 men and 3 women, out of all 30 students. And so 5 divided by 30 is 0.1667. So in this class, about 17% of the students got an A. Okay, now for part C, notice this word or. That's how we're going to know to use the addition rule. Find the probability that the student is a woman or received an A. So we're looking for the probability of woman or A. So using the addition rule, that's going to be the probability of a woman plus the probability of an A minus the probability of being a woman and an A at the same time. Okay, well, the probability of being a woman, we saw that earlier. That was 17 out of 30. I find you could use the decimals here, but since you can plug everything into your calculator, you'll get more accurate answers if you leave them as fractions until the very end. The probability of getting an A was 5 out of 30. Minus, now notice what's happened here is we've counted all the women and we've counted all the A's. And some of the women got A's, so we've double counted. So we need to subtract that out. So how many women got A's? That's 3. So we counted those 3 women twice. So it's going to be minus 3 out of 30. And so 17 plus 5 is 22. 22 minus 3 is 19 out of 30. And so if you divide that and make it a decimal, we get 0.6333. So if you randomly select one student, the probability that it's a woman or someone who got an A is about 63%. Okay. I think there's one more part to this one. Part D, find the probability that the student did not receive an A. Well, notice here that we're looking at the opposite of getting an A. So we could think of this as the probability of A complement, that they did not get an A. And that will be 1 minus the probability that they did get an A. So the probability that they did get an A was 5 out of 30. So that's going to be 1 minus 5 out of 30. And you don't have to be super good with fractions and stuff. You can just type it right in your calculator. 1 minus 5 out of 30 is going to give you the decimal equivalent. So it's 0.8333. And so that's the probability that one randomly selected student did not have an A. Okay, let's go on to number 42. I think this is our last example here. It's on flawed parts. On a certain day, a foundry manufactured 500 cast aluminum parts. Some of these had major flaws, some had minor flaws, and some had both major and minor flaws. The following table presents the results. Okay, this is what we call a contingency table, and we'll talk some more about contingency tables near the end of the semester. But with contingency tables, it's almost always very helpful to have an extra column, sometimes and an extra row as well. Sometimes they'll put this in for you, but sometimes you have to create it yourself, and that's the totals. So it's helpful to have totals. Okay, so for the minor flaw, there were 95 total. For the no minor flaw, there were 405 total. Major flaw, there were a total of 55. And no major flaw, 75 plus 370, there's a total of 445. And it should always be the case that the grand total ends up in this little box right here. So if I take 55 plus 445, I get 500. And also if I take 95 plus 405, I get 500. Notice they said that they manufactured 500 total. Okay, so this table we can use to calculate some probabilities. So the first one says, find the probability that a randomly chosen part has a major flaw. So for here, we're just looking for the probability of major. Sometimes you're not going to have to use anything other than just the basic probability formula, which is the number of ways the event can occur divided by the total number. And that's the case here. So the number of major flaws total was 55. And that's including some that had minor flaws and some that didn't have minor flaws. And that's out of 500. And so if you divide that, you're going to get 0.11. So that's the probability that it has a major flaw. Okay, part B is find the probability that a randomly chosen part has a minor flaw. So we want the probability of minor. Well, I'm going to add down the first column. You can see that there were 95 total that had a minor flaw. Some of them had a major flaw as well, but 95 total had a minor flaw, and that's out of the grand total 500. And so if you take 95 divided by 500, we get 0.19. So that's the probability that it has a minor flaw. Okay, and then for part C, it says find the probability that a randomly chosen part has a flaw. It could be major or minor. So we want the probability of major or minor. Well, or is that big red flag that you want to use the addition rule. So that's going to be the probability of major plus the probability of minor minus the probability of major and minor at the same time. And remember, if that last number is 0, they're mutually exclusive. Now we know that's not going to be the case here. They told us right in the problem that sometimes some of the parts have both flaws. Okay, so the probability of a major flaw, we found that in part A, that was 55 out of 500. Plus the probability of a minor flaw, we found that in part B, that was 95 out of 500. Minus, now this is also going to be out of 500, but we want to count how many have both types of flaws. So I need to go back and look at my chart, and we're looking at where this row, major flaw, and this column, minor flaw, intersect, and it's right here at 20. So 20 of the parts had both a major and a minor flaw. So that's going to be minus the 20 out of 500. Now you can just type these three fractions into your calculator. 55 divided by 100, I'll show you. 55 divided by 500 plus 95 divided by 500 plus, or no, I'm sorry, minus 20 divided by 500. And you can get the answer that way. It's 0.26. Or, since all of these have the same denominator, you could just add and subtract the numerators and just divide by 500 once. So 55 plus 95 is what? 150 minus 20 is 130. So we could also do it that way. 130 divided by 500 should give us the same thing, 0.26, which it does. So either way. When you're using, this is a common mistake I see, so I'd like to point this out to help you find mistakes. Whenever you're using the general addition rule, all of your denominators, all three of them, will always be the same thing, as long as you haven't reduced your fractions. So sometimes this last one here, students change the denominator, they get confused, but they're all going to be out of the grand total. They're going to have the same number. All right, and then the last part, and I believe this is next to the last part, sorry, is find the probability that a randomly chosen part has no major flaw. So we want the probability of no major. Now we could go do this directly and count how many don't have a major flaw, and you can do that, that's fine. But I think it's probably easier, since this is a complement, it's the opposite of having a major, to just use the rule of complements. So it would be 1 minus the probability of major. So that's going to be 1 minus, and the probability of a major flaw was 55 out of 500. And so if you do that arithmetic, you're going to get 0.89. And so that's the probability that it does not have a major flaw. All right, and then finally, well, actually, let me show you how you could do this directly, just so you can see it both ways. So an alternate way to do this would be for the probability of no major, you could just go back to your table and count how many do not have a major flaw. So no major flaw is 445. So I actually already did the counting there. So you could also just do 445 out of 500. And if you do that division, you'll see you get the same answer. So either way is fine. Like I said, there will be instances later where it's way, way easier to use the rule of complements than to do it directly. But this isn't one of them. All right, and then finally for part E, find the probability that a randomly chosen part has no flaw. Well, the probability of no flaw, here, this is probably an example where it might be easier to use a complement, would be 1 minus the probability that it has a flaw. And that's what we calculated in part C. Because remember, in part C, it was find the probability that a randomly chosen part has a flaw. So either major or minor. And so that was 0.26. So we could do 1 minus the 0.26. Oops, my screen is acting weird. Okay, 1 minus 0.26, and that's going to give us 0.74. And so that's the probability that it doesn't have a flaw. Okay, that finishes up section 5.2. In the next video, we'll look at 5.3, which is on the multiplication rule, which deals with and probabilities. But the big distinction is going to be that we're selecting more than one item. And so that's what's in the next video.